Hello everyone, this is movie clip number 5 for the second week. So in this movie clip, I'm going to begin with the details on how to understand charge carrier concentrations. On the, as described in this lecture note, N sub D indicates fully ionized donor concentration. A ionized donor concentration. So basic assumption for this notation is N sub B is identical to the N sub D plus. 100% donor atoms are ionized. Okay, so that is a basic assumption in this device physics. And acceptor is identical. N sub A is identical to the N sub A minus. Okay, so all the acceptors are fully ionized, which was negatively charged. So, uh, in silicon materials, a crystalline silicon material, which is doped with donors as well as acceptors, those two conditions are satisfied. Number one is charge neutrality conditions. For a given silicon sample, which is doped with acceptor and donors, the total amount of positive charge should be equal to the total amount of negative charge. So on the left-hand side, in this equation, Nd plus and positive hole concentration indicates the total amount of positive charge coming from the holes, right? So on the left-hand side, you can see that whole bunch of positive charge. And on the right-hand side, you can see that the negative charge stuff, right? And indicates electron concentration. So, you know, Na minus is negatively charged electric concentration. So Na plus N indicates the total amount of negative charge. So always, for a given sample, the total amount of positive charge should be well balanced to the total amount of negative charge. So this charge neutrality condition should be always satisfied for any type of material. And second equation that we are going to learn is at thermal equilibrium. The thermal equilibrium means no external force. Under no external force, in other words, at thermal equilibrium, so without any external forces applied to this silicon sample, then we can say that this sample is at thermal equilibrium. So we will learn some more details, the physical meaning of the thermal equilibrium in the end. But at this point, please remember that there is no external force, no voltage, no electric field, magnetic field, no light, and no mechanical stress. Those are all types of externally applied forces are not included. At thermal equilibrium, uh, total number of electron concentration times hole concentration should be equal to a constant, which is n sub I square. So I said this is a constant. Okay, so n sub I was 10 to the 10 per cubic centimeter for crystalline silicon material. Okay, and N is total electron concentration, P is total hole concentration. So in pure silicon or in intrinsic silicon, right? Electron and holes are created in pairs, right? EHP. So electron concentration is equal to the hole concentration, and those two numbers are identical to the N sub I. So here N sub I indicates the intrinsic carrier concentration, right? So the real number of the N sub I was 10 to the 10 per cubic centimeter. From this equation, we can derive this equation. N times P is equal to Ni times Ni. That is equal to Ni square. So this n times p is equal to n sub I squared, or 10 to the 20. Okay, so note that this number has been obtained at room temperature or at 300 Kelvin. Okay? So with temperature increasing, the value of n sub I is also increasing. Okay, and all this number is is for silicon crystalline material. Okay, all right. So now let's number those two equations, one and two. Take a look at the equation 1 and 2. N sub D, N sub A, that is, we know the impurity concentration. And N sub I squared at room temperature 10 to the 10 over square. So we have two unknown variables, P and N, right? Here P and N. And the other uh, terms are constant, or the value that we can control. Okay, so you can solve those two equations systematically together, and you're gonna get the solution for n and another solution for p. Okay, then you can solve those two equations, first order two equations, systematic two equations. Okay, then you're gonna end up with those two solutions. Okay, but it looks like a very complicated. Those two solutions looks complicated. Okay, so in the upcoming lecture note, we're gonna simplify those two solutions. Okay, and we're gonna see some details of what the N-type silicon material is and what the P-type silicon material is. We're gonna learn this soon. And here, one note is carrier concentrations depend on net dopant concentration. So carrier concentration means total amount of electron and total number of hole. Those are very dependent of net dopant concentration. So suppose that we have a pure silicon sample, and here we're gonna put donors as well as acceptor together. Say that n sub d is a 10 to the 16 per cubic centimeter, and n sub a is 10 to the, I would say, 5 times 10 to the 15 per cubic centimeter. Then, uh, you know, the number of donor is 10 to the 16, the number of acceptor is 5 times 10 to the 15, which means zero point 0.5 times 10 to the 16, which means 50% of, in terms of the number of acceptors and donors, 50% of donors concentration is identical to the acceptors concentration. So in effect, effectively, ND minus NA is equal to 10 to the 16 minus 1 half times 10 to the 16. Therefore, 1 half times 10 to the 16, which is 5 times 10 to the 15. So this, the acceptor, the amount of acceptor can cancel out. You know the meaning of cancel out or compensate the half amount of donor concentration. So the other half left behind can work as net dopant concentration. Okay, so suppose that for given pure silicon sample, you put the donors as well as acceptors together, but the amount of donor is 10 to the 16. The acceptors, the amount of acceptors is 5 times 10 to the 15, which is a half of the uh, donor stopping concentration. Then, from the perspective of this pure silicon material, it has adopted 5 times 10 to the 15 donors concentration. So whenever we are talking about the electron concentration and hole concentration, previously I mentioned that donors concentration would govern the total amount of electron, and acceptors concentration would govern the hole concentration. But what if donor acceptors are put together for a given pure or intrinsic silicon material, then we should take into account those donors and acceptors together. So in that sense, net dopant concentration, Nd minus Na, or in some case, if Na is higher than Nd, then Na minus Nd. Those net dopant concentration is really key factor in determining carrier concentrations, that is electron concentration and hole concentration. Okay, so herein I would like to show you some examples for antimaterial. So for given silicon material, definitely crystalline silicon material, you put the donors and acceptors together. Then the net dopant concentration is n sub d minus n sub a, which is way higher than the n sub I, that which is 10 to the 10 per cubic centimeter. Okay? So in this case, what is a electron concentration and what is a hole concentration in this specific silicon material with donors and acceptors together? But donor concentration is much higher than the acceptor concentration. Question is, what is electron concentration? What is hole concentration? As I just explained you in the previous slide, the area concentration, such as electron concentration, hole concentration, very depend on the net dopant concentration. So net dopant concentration is n sub d minus Na. Here in the Nd is higher than Na, so I use the Nd minus Na. Then that is, some part of the donor will be compensated by the total amount of acceptor concentration. So the leftover of donor concentration will create the free electrons, right? So that the electron concentration and small n will be governed by Nd minus Na. But usually, Na is much smaller than donor concentration, right? So on purpose, device and process engineer would implant 10 times higher donors than the acceptor concentration. For example, N sub D is 10 to the 18 per cubic centimeter, and N sub A is, say, 10 to the 17 per cubic centimeter. And in this case, we are engineers, right? So ignore this a small number because it is 1/10 of the donor's concentration, right? 10 to the 17 is 1/10 of the donor concentration, so that Nd minus Na in this case is simply Nd, which is 10 to the 18 per cubic centimeter. So from now on, you can think of this sample with 10 to the 18 donors concentration. If I do some complicated mathematics, then you should claim that Nd is even though we plug in 10 to the 18 donor atoms, but part of it exactly 10 to the 17 out of 10 to the 18. Those 10 to the 17 donor atoms are used to cancel out and compensate the 10 to the 17 acceptors. That's true. I know, yeah, that's true. But however, we can ignore it because this 10 to the 17 is much, much lower than the 10 to the 18 total amount of donor concentration. So in this lecture or in midterm final exam, if a certain value is smaller than the original value by 10 times, then ignore it. Okay. All right. So now we suppose that this sample is doped with donors with a 10 to the 18 per cubic centimeter. Then you can simply speaking that you can simply say then total free electron concentration is identical to the donor's concentration, so that the electron concentration N is equal to the Nd. But in more exact form, it should be Nd minus Na. Okay, right. So we we now found the electron concentration. What about the whole concentration in this uh, donor doped silicon sample? In the previous lecture note, we have learned one equation, that is n times p is equal to the constant. Okay? that constant value is 10 to the 20, right? Because the n sub I is 10 to the 10. So since we know the electron concentration as n sub d, that is 10 to the 18, then you can plug in this value into the n, then you're gonna find out the whole concentration. So in this case, the whole concentration is 10 to the 20 divided by 10 to the 18. So the answer is 10 to the 2 per cubic centimeter. Okay, so in 1 cubic centimeter, you can find out 100 holes, and in 1 cubic centimeter, you can find the 10 to the 18 electrons. You can now feel how big the difference is in between electron concentration and hole concentration. Right. So here, antimaterial physically means silicon sample with lots of electrons. Okay, so that is n-type silicon material. Some people are saying that this is n-type, then you always think of, this silicon sample has a bunch of donor atoms compared against the acceptor materials, so that it has a tremendous amount of free electrons. And that electron concentration is totally controlled by donor's concentration, because donor is more implanted into the silicon material. What about the p-type material? Well, everything is just simply opposite. Now, acceptor concentration is much higher than donor's concentration, so net dopant concentration is Na minus Nd, and definitely which is much higher than the 10 to the 10 intrinsic carrier concentration. So, uh, for a pure silicon material, at room temperature, it has a 10 to the 10 electron and 10 to the 10 of holes. That's basic. Fundamentally, it has a 10 to the 10 electrons and holes together. However, now for a pure silicon material, we plug in acceptor and donor together. But in this case, acceptor is much higher than the donor concentration. What would be happened? The question is, what is a final hole concentration? What is the electron concentration? Let's do this again. Part these donors, which is much smaller than the Na. So part of the Na will be used to compensate and cancel out the donors, right? So part of the acceptor will be used to create the holes, right? However, Na is much higher than Nd, so we can simply say that Na itself can be used for what? To create holes, right? How many holes we can create from Na? Well, as we have learned, single acceptor will create a single hole. So the hole concentration should be identical to the hole concentration. But that, technically speaking, the instead of Na minus Nd is more exact form. However, Nd is much smaller than Na, so we can ignore the term of Nd. Okay, so in more exact form is Na minus Nd. Okay, but if I give you the number, say Na is 10 to the 18, Nd is 10 to the 16, then you can simply say that the whole concentration is 10 to the 18, because 10 to the 16 is 1/100th of the 10 to the 18. So ignore this number. We are engineer. And what about the electron concentration? Using the n times p is equal to n sub y squared. So plug in those numbers, 10 to the 10 squared times the whole concentration, 10 to the 18. So in the end, electron concentration is per cubic centimeter 100. So in this sample, I mean the acceptor concentration is much higher than donor concentration. Then this silicon material is p-type because it has tremendous amount of holes, saying 10 to the 18, which is identical to the acceptor concentration. And what about the electron concentration? That is just simply 100, which is way smaller than the whole concentration. So p-type silicon material means it has a bunch of holes, compared against the electron. Electron is very rare material, and in previous lecture of the anti-material, the most abundant carrier was electron. Okay? So herein you can see a short summary for terminologies that we are going to use in this lecture. So donor indicates an impurity atom coming from column 5 in periodic table, and the role of donor is to increase electron concentration. So single donor will give us single free electron because it has one more extra uh, outermost electron compared against the silicon atom, right? So donor can give us uh, one more free electron. So yeah, you can simply understand this sentence. And what about the acceptor? Acceptor is the other type of impurity atom coming from the column 3 periodic table, which can increase the whole concentration. So single acceptor will contribute to create single hole. So if you know the whole acceptor concentration, you can simply estimate quantitatively the whole concentration. So again here, once you know the acceptor, that is corresponding to the whole concentration. Once you know the donor concentration, you know the N. But this is the example that we have just gone over. The ND and NA are both together implanted into the silicon material. And how to calculate the N and P? Uh, First, determine which value is higher. Okay? For example, ND is higher than NA. Then part of the donor will be used to cancel out the acceptors so that left uh, the donor concentration left behind after compensating acceptors will be used to create the electron. So N is simply Nd minus Na, but most likely Na is much smaller than Nd, so you can ignore it. Then, using the equation N times P is equal to Ni squared, and you can calculate the whole concentration together. So in this case, electron concentration is more abundant than the whole concentration. And we can say that this silicon material is anti-material. Okay. So basic idea of anti-material is anti-material can have more electrons than holes. And p-type material, it is opposite. P-type material has more holes than electrons. Type P-type material, donor, acceptor. Okay. And this is a new terminology, majority carrier, minority carrier. So majority carrier indicates the most abundant carrier. So the question is as follows. What is the majority carrier in antimaterial? In antimaterial, it has more electrons than holes, so that majority carrier of antimaterial is electrons. Okay? What about the minority carrier? The meaning of minority carrier is the least abundant carrier. Okay? So, what is the minority carrier in p-type material? Well, we have learned that p-type material contains more holes than electrons, so that minority carrier of p-type material is electrons, right? So you can simply answer those two questions if you can understand the concept of majority versus minority carrier. Okay, the last one, intrinsic versus extrinsic. So the meaning of intrinsic is identical to the pure. Okay, so pure semiconductor or intrinsic semiconductor means that without any open atom, silicon itself has been used to make crystalline silicon material. In this case, electrons and holes are created together in pairs so that electron concentration should always be equal to the whole concentration as the constant of n sub I, which is 10 to the 10 per cubic centimeter at room temperature, 300 Kelvin. Okay? And what about the extrinsic semiconductor? Extrinsic means, simply speaking, doped semiconductor. Okay? An intrinsic semiconductor is now doped with an acceptor and donor, then we can say that this semiconductor is extrinsic material or doped semiconductor. In this case, electron concentration N can be determined by n sub d minus Na if Nd is much higher than Na. And what about the whole concentration in this material, doped semiconductor material, whole concentration can be simply determined with using this equation. N times P is equal to Ni square. Okay, so Nd minus Na Ni square. Okay. So here I would like to mention the name of the equation. N times P is equal to Ni square. That is named as action mass action law. Okay, so using mass action law, we can estimate the hole concentration or electron concentration if we know the electron hole concentration uh, throughout throughout knowing the donor and acceptor concentration. Mass action law. But you could say I would like to put some more emphasis that this n and p value has been obtained at thermal equilibrium. So I put some subscript not uh, as a subscript for n and p. And n naught times p naught is equal to ni squared. But for a while, for the time being, I'm going to use np is equal to ni squared because we uh, maybe for the very first a few weeks, several weeks, I will not tell about some non-equilibrium status. Okay, so everything is uh, explained under thermal equilibrium. So that this subscript not doesn't mean anything, I guess, for a while. But when we have a chance to learn the PN junction diode and others, MS diode, the Schottky diode, the equilibrium versus non-equilibrium is quite important. Okay? So at that point, we're gonna write down the mass action law as n naught times p naught equal to ni squared. Okay. All right. For a while, you can say that NP is ni squared, but to to you know to say that to explicitly say this mass action law is valid at thermal equilibrium, then you should take a note, not as a subscript for NMP. Okay, here is a short summary. Uh, Bandgap energy. We have learned the bandgap energy of silicon as described here, 1.12 electron volts at room temperature. Okay, the meaning of the bandgap energy is the minimum required energy to have an electron free out of the covalent bond. And uh, semiconductors have a relatively small value of bandgap energy, but insulators such as silicon dioxide, has large bandgap energy that is about 9 electron volt. And the second theme of this lecture note was dopant atoms in silicon. So the basic meaning of dopant means it should reside on lattice site. In other words, the silicon atom is substituted with dopant atoms. Because the reason why I'm saying this again is let's take a look at this situation. Silicon atoms are bonded tightly, and boron atom has been included in this pure silicon material, but it cannot make any uh, bond. Can you still say that this boron is working as an acceptor in pure silicon material? Maybe yes or maybe no. Think about this point. This is quite good question for midterm exam. But here is answer. As long as boron atom is fully replacing, substituting the silicon atom at lattice site, I'm talking about this site, the silicon atom site, the role of boron is nothing. Even though boron itself has been included in pure silicon crystalline material, the role of the boron atom is useless, so that this silicon material is not doped with boron atoms electrically. Physically, the silicon material has contains the boron acceptors. However, the boron atom is electrically not activated in a silicon material. So we can say that electrically speaking, the silicon material is not doped at all because the boron atom has not completed to make up bonds between four neighboring silicon atoms in a silicon crystalline material. Okay, think about this point. Quite good. So that's the reason why I'm saying acceptor concentration is equal to the Na minus. This assumption, full ionization, is based on that all the boron atom can have some kind of bonds. If boron itself is simply included in a silicon material without any covalent bonds with the four neighboring silicon atoms, then this equation should not be correct. It should be like that. Na is not equal to Na minus. Maybe Na is slightly higher than Na minus. Part of the acceptor is ionized. As a result, part of the acceptor has a full covalent bonds with the four neighboring silicon atoms. Okay, second bullet group 5 elements contribute conduction electrons and are called the donors, right? So the impurity atom coming from group 5, column 5 in periodic table can become donor. And here, group 3 elements such as boron enables to contribute holes and are called acceptors. And very low ionization energies, smaller than 50 millielectron volt, is necessary to have all the dopant atoms, donors, acceptors to be ionized at room temperature. Okay, all right, that's all. And the last message in this movie clip is the dopant concentration, typically in the range from 10 to the 14 to 20. So why this is very significant? Previously, we have estimated the atomic density of silicon. Right? That was 5 times 10 to the 22 per cubic centimeter. So this is the upper limit of the doping concentration. However, the solid state solubility of the donors and acceptors is slightly lower than this atomic density of silicon. That is usually 10 to the 20 up to 21. Okay. So whenever you have your job responsibility is to choose or uh, to make a list of candidate materials for doping silicon material, one of the consideration in determining the dopant atoms is solid state solubility. The higher solid state solubility it is, the better it is. Why is that? Because the more doping concentration indicates that the more number of electrons or holes are available in flowing current using that doped semiconductor. Okay, so anyhow, the doping concentration is upper limited by atomic density of silicon or solid state solubility. What about the lower boundary of the doping concentration? Herein I use the 10 to the 14. Why 10 to the 14 instead of 10 to the 10? 10 to the 10 is corresponding to the n sub I, right? N sub I means without any dopant atoms, the silicon material can have free electrons and free holes at room temperature. Because of the externally applied thermal energy, a few electrons becomes free and the holes are left behind. So electron pairs are created together in pairs. So the total number of free electron and holes are up to 10 to the 10 at room temperature. But doping concentration is now 10 to the 14 instead of 10 to the 10. Why is that? That is very associated to the some processing step for fabricating silicon substrate or or wafer. In fabricating silicon wafer, we are using a crucible, big, chunk of kind of dish, okay, big chunk of dish. Uh, the material consisting of this big chunk of dish or crucible is p-type doped. So some tiny amount of p-type dopant atoms are smeared into the liquid state of the pure silicon material. So after uh, pulling out the solid state silicon material, which is named as ingot, uh, the part of the p-type dopant atoms are included so that the minimum number of dopant atom is 10 to the 14 in cost-effective p-type silicon sulfate. For mass production, cost is the key uh, key metric so that the cheapest, the lowest amount of cost in fabricating silicon substrate uh, is a p-type silicon substrate. So 10 to the 14 is the minimum, lower boundary in terms of implementing doping concentration. So, remember the typical range of doping concentration from 10 to the 14 to 10 to the 20. I would say 10 to the 20, up to 10 to the 21 is possible in cutting edge semiconductor process and steps. So 10 to the 14 to 10 to the 21, which is reasonable, typical range of doping concentration. Okay, that's all for the movie clip part 5 for second week. See you in the next movie clip.